On Monday, the storm was a disorganized cluster of thunderstorms spinning at just 45 knots, about 52 miles an hour, with a central pressure of 996 millibars. By Tuesday, it was flirting with super typhoon status at 125 knots. And by Wednesday, forecasters were penciling in sustained winds of 180 miles an hour with gusts over 210. That is not a typo, and it is not an exaggeration. That is the actual documented advisory by advisory progression of a storm that meteorologists are now calling one of the most aggressive rapid intensification events of the year. Its name is Dolphin, and if you have not heard of it yet, you are about to, because what is happening in the middle of the Pacific Ocean right now is the kind of thing that makes career storm chasers stop mid-sentence and stare at their screens. Let's start with where this thing actually is, because the location matters almost as much as the numbers. Dolphin formed far out in the western Pacific, thousands of miles from any coastline that most people could point to on a map. When it was first designated as a tropical depression, it was sitting northeast of the Marshall Islands in a stretch of open ocean that most of us will never sail across and never think about, unless a storm like this one forces us to. A few days later, it was closing in on Wake Island, a tiny American outpost in the middle of nowhere, a spit of coral and pavement that exists mostly as a refueling stop and a military waypoint. That is the audience Dolphin had for its opening act: empty water, one remote island, and satellites. But empty water does not mean an empty story, because what has happened to this storm over the last few days is exactly the kind of event that reshapes how we think about hurricane and typhoon season, how we prepare for it, and how much warning we can realistically expect the next time an ocean basin decides to misbehave. So let's slow down and walk through it, step by step, using the actual advisory data that forecasters have been publishing in real time. The first official advisory on this system described a tropical storm with winds of 45 knots, a central pressure of 996 hectopascals, and a forecast trend labeled, in the dry language of meteorologists, as steady to rapid strengthening. At that point, the storm was moving west at about 15 knots, roughly 17 miles an hour, drifting across the far eastern portion of the western Pacific Basin. Even in that first advisory, there were warning signs buried in the technical language. Convective banding, the spiraling bands of thunderstorms that wrap around a storm's center, was becoming more discrete and organized. Microwave satellite imagery, which can peer through the outer cloud shield and see the structure underneath, was already hinting that an inner core was forming. Forecasters even noted what looked like a developing eye feature on visible satellite images just before dusk. In hurricane forecasting, an early eye feature during the tropical storm stage is a red flag. It usually means the storm is not just strengthening, it is strengthening in a hurry. Within about 24 hours, that hunch was confirmed. The storm's radial outflow, the exhaust system that vents warm air away from the top of the storm and allows the engine underneath to keep running efficiently, was described as strong in all quadrants. The banding kept tightening, and true to the forecast, the storm crossed the threshold into typhoon strength roughly on schedule, becoming what forecasters in the region call a typhoon, the same category of storm that in the Atlantic we would call a hurricane. Same physics, same intensity scale, different regional name. Then things accelerated in a way that even seasoned meteorologists described as remarkable. Within roughly 48 hours of reaching typhoon strength, the storm had already climbed to 125 knots, which put it just below the threshold for super typhoon status. One meteorologist who has tracked tropical systems professionally for years described the storm as having undergone an eye wall replacement cycle, a process where a storm briefly stalls in its intensification because a second outer ring of thunderstorms forms around the original eye wall and temporarily disrupts the storm's structure. This is common in very powerful storms, and it usually signals that the storm is not weakening. It is reorganizing before making another run at greater strength. Sea surface temperatures across the storm's path were sitting between 30 and 31 degrees Celsius, roughly 86 to 88 degrees Fahrenheit. To put that in perspective, typical guidance used by hurricane forecasters suggests that ocean temperatures need to be around 26 or 27 degrees Celsius to sustain a tropical cyclone. This storm was moving through water that was several degrees warmer than the minimum threshold, across a massive expanse of ocean, which meant it had fuel to burn and nowhere for that fuel to run out anytime soon. By the time the storm was approaching Wake Island, official forecasts from the agency responsible for tracking Pacific typhoons were projecting continued intensification, with wind speed estimates reaching as high as 155 knots within 72 hours. That works out to roughly 178 miles an hour. Independent tracking services, pulling from satellite-derived wind estimates, were already reporting sustained winds around 145 to 150 knots and gusts near 170 knots, converting to wind speeds in the range of 265 to 285 kilometers an hour, or roughly 165 to 177 miles an hour. On the Wednesday morning update, one national meteorological outlet described the storm passing near Wake Island with sustained winds of 140 miles an hour, already a major typhoon by any measure, and forecasts calling for it to reach somewhere between 170 and 180 miles an hour at peak strength. Let's put that number in context, because 180 miles an hour is not just a big number, it is a specific and terrifying threshold. Meteorologists have compared wind speeds in that range to the force generated by an EF4 or EF5 tornado, the strongest tornadoes that exist, capable of leveling well-built structures and turning debris into airborne projectiles. The difference between a tornado and a storm like this one is duration and scale. A tornado might sustain that kind of violence for a few minutes, over a path a few hundred yards wide. A storm like this one can sustain winds in that range for hours, across a footprint that can stretch for dozens of miles, and it can do so continuously as it crawls across the ocean for days at a time. So how does a storm go from a disorganized tropical depression to something with the punch of a violent tornado in less than a week? The honest answer is that meteorologists study this exact question constantly, because rapid intensification, the technical term for when a storm's winds increase by 35 miles an hour or more within 24 hours, is one of the hardest things to forecast precisely and one of the most dangerous phenomena in the entire field of tropical meteorology. This particular storm didn't just meet that threshold, it blew past it, gaining far more than 35 miles an hour of wind speed in a single day at multiple points during its life cycle. The ingredients for rapid intensification are, in principle, simple to describe, even if predicting exactly when and how fast they will combine is fiendishly difficult. You need warm water, and not just warm at the surface, but warm to a significant depth, because a storm's own winds churn up the ocean beneath it, and if that churning pulls up cooler water from below, it can choke off the storm's fuel supply. You need low wind shear, meaning the winds at different altitudes in the atmosphere are blowing in roughly the same direction and at similar speeds, because shear tends to tear a storm structure apart before it can organize a tight, symmetric core. You need a moist atmosphere, because dry air getting pulled into a storm circulation disrupts the thunderstorm activity that powers the whole system. And you often need good upper-level outflow, that exhaust system mentioned earlier, allowing the storm to continuously vent the rising air at its center, so the engine keeps running without backing up on itself. This particular storm found nearly all of those ingredients in generous supply. The sea surface temperatures across its path were running well above the threshold needed to sustain a cyclone, and forecasters specifically flagged a massive expanse of water in the storm's forecast path sitting at 30 to 31 degrees Celsius, which is about as favorable as ocean temperatures get for this kind of explosive development. El Niño years often produce warmer than typical sea surface temperatures across large stretches of the Pacific. And this year, forecasters have specifically noted that waters in parts of the eastern and central Pacific are experiencing near record warmth for this point in the season, a reflection of how early and how strong this El Niño pattern has developed. It's worth pausing here to note that this storm is not happening in isolation. This has been an unusually active stretch for the Pacific Basin as a whole, on both sides of the international dateline. A third storm, a hurricane that had been trending toward the Hawaiian Islands, was also active during this same window, moving on a track that would bring it near or north of the islands, though with weakening intensity by the time it arrived in that vicinity. 3 storms, active at essentially the same time, across 2 ocean basins, with at least 2 of them undergoing rapid intensification within days of each other. That is not typical. That is not what a routine stretch of hurricane season looks like. One meteorologist summarized the situation with a simple phrase, describing the Pacific as sizzling, while the Atlantic, by contrast, was simmering along at a much quieter pace. That contrast matters, because it tells us something about where the atmosphere's attention has been focused this year, and El Niño is very likely playing a central role in that redistribution of energy and moisture. Let's go back to the storm at the center of this story and talk about what happens next. Because forecasting where a storm like this goes, and how strong it will be when it gets there, is where the science gets genuinely uncertain, even with all the satellite data and computer modeling available today. But forecasters have been explicit that it is still too early to say with confidence exactly where the storm will end up making its closest approach to land, if it makes one at all in a way that produces significant impacts. Different modeling systems have shown some disagreement, with one high-resolution hurricane model reportedly experiencing numerical stability issues trying to properly resolve the storm's extremely compact and intense structure, sometimes described using the vivid image of a buzzsaw, a tightly wound symmetric core spinning at tremendous speed. That level of structural intensity, sometimes visible on satellite imagery as what meteorologists call a pinhole eye, a tiny well-defined center surrounded by extremely intense thunderstorms, is often associated with storms that are either at or very near their peak intensity, but it also makes them structurally fragile. A pinhole eye can collapse and reform through an eye wall replacement cycle relatively quickly, causing intensity to fluctuate even as the storm remains an extremely dangerous system overall. Forecasters watching this storm noted exactly that kind of fluctuation, describing how the storm looked spectacular on one set of images, only to have its eye become obscured within the following hour as the internal structure shifted. This is part of why short-term intensity forecasts for the most powerful storms can shift by 10 or 20 miles an hour from one advisory to the next, even when the overall trend, in this case continued strengthening, remains consistent. Independent probability guidance published alongside the advisories put the odds of another eye wall replacement cycle within the following 24 hours, at a meaningful, though not overwhelming percentage, allowing for the kind of short-term ups and downs in intensity that makes storms like this one so difficult to summarize in a single headline number. The honest picture is less like a smooth curve climbing toward a single peak, and more like a jagged staircase with bursts of explosive strengthening punctuated by brief pauses or minor wobbles as the storm's internal structure reorganizes itself before continuing to intensify. What does remain fairly consistent across the forecasts is the broader environmental picture. The atmosphere and ocean around this storm remain supportive of continued strength for the near term, with warm water extending well ahead of the storm's projected path, low to moderate wind shear, and a moist atmospheric environment. Forecasters have specifically flagged the possibility that peak sustained winds could reach somewhere in the range of 170 to 180 miles an hour, with gusts potentially exceeding 210 miles an hour, values that would place this storm among the most intense tropical cyclones observed anywhere on the planet this year. For context, storms of this magnitude are sometimes referred to using the term super typhoon, a designation used once sustained winds reach roughly 150 miles an hour, equivalent to a strong Category 4 or Category 5 hurricane on the scale used in the Atlantic and Eastern Pacific. Reaching that threshold puts a storm in a fairly exclusive club. Most tropical cyclones never come close to this level of intensity. The vast majority of named storms in any given season top out somewhere in the tropical storm or Category 1 range, produce their impacts and dissipate without ever approaching the kind of sustained violence this storm has already demonstrated. It's also worth noting how quickly this storm has cycled through the naming and categorization process that meteorologists use to communicate risk. It started as an area of disturbed weather, got picked up by forecasters as a system worth watching, was designated as a tropical depression. Once it developed a defined center of circulation, was upgraded to a named tropical storm once its winds crossed the threshold of 39 miles an hour, and then crossed into typhoon status once winds exceeded 74 miles an hour. Bases in the region have maintained a seasonal readiness posture appropriate for tropical cyclone activity, a standard precaution during a season when multiple systems have already required monitoring. Wake Island itself, given its small size and limited infrastructure, is particularly vulnerable to any storm passing close enough to bring its strongest winds ashore, even briefly, which is part of why forecasters have been tracking the storm's exact path relative to the island so closely in each successive advisory. Beyond the immediate vicinity of the storm's current position, the larger question hanging over the system is where it ultimately ends up and what happens when, or if, it interacts with more densely populated coastlines. Long-range forecast tracks have shown a broad envelope of possible paths extending toward East Asia, with southern Japan and areas of coastal China among the regions falling within the range of outcomes shown by ensemble model guidance. But a broad envelope of possible paths is exactly that, broad. And it would be inaccurate and irresponsible to declare with confidence today exactly which coastline, if any, will bear the brunt of this storm's most extreme winds. This is a useful moment to step back and talk about why storms like this one matter beyond the raw spectacle of the numbers. Because it's easy to get swept up in phrases like 180-mile-an-hour winds and lose sight of what that actually means in practical terms. Wind speeds in that range are capable of causing catastrophic structural damage to nearly any building not specifically engineered to withstand them. They can snap power poles, uproot mature trees, tear roofing systems off buildings, and turn ordinary debris into dangerous projectiles. When storms of this intensity make landfall, or pass close enough to bring their strongest wind fields ashore, they can cause damage comparable to a wide swath of simultaneous, sustained tornado force winds, rather than the brief, localized violence of a single tornado touchdown. That is part of why meteorologists reach for comparisons to EF4 and EF5 tornadoes when trying to communicate the scale of danger a storm like this represents. Even though the physical mechanisms producing the winds are different, there is also the secondary threat that storms like this one bring regardless of their peak wind speed at any given moment, and that is the ocean's response to a powerful storm passing overhead. Storms of this magnitude generate significant swells that radiate outward from their center for hundreds, sometimes over 1,000 miles, arriving at coastlines as dangerous surf, rip currents, and elevated surge, even in places that never experience the storm's wind field directly. This is part of why hazard messaging around powerful tropical systems often extends far beyond the immediate forecast track. urging caution along coastlines that may be nowhere near the storm's projected path, but could still see hazardous marine conditions in the days that follow. If this storm does eventually approach more populated coastlines in East Asia, the region has extensive experience managing typhoon impacts, given how frequently the Western Pacific Basin produces powerful storms during this stretch of the calendar. Even so, a storm capable of sustaining winds in the 170 to 180 mile an hour range represents a serious hazard regardless of how well prepared a region generally is. And forecasters, disaster management agencies, and local governments in any potential path would be closely monitoring subsequent advisories as the picture becomes clearer over the coming days. Let's return for a moment to the broader pattern this storm fits into, because understanding the context helps explain why this particular typhoon season has already produced multiple storms capable of this kind of explosive strengthening. Rapid intensification events, broadly speaking, are not new. They have always been part of tropical meteorology, and history is full of storms that surprised forecasters and coastal communities by strengthening far faster than anticipated in the final day or two before landfall. What has changed, according to ongoing research within the meteorological community, is the frequency and magnitude of these events, particularly as ocean heat content, the total amount of warm water available beneath the surface, has trended upward in many tropical basins over recent decades. Warmer oceans provide more fuel and more consistently available fuel for storms attempting to intensify rapidly, which some researchers argue is contributing to an increase in the number of storms that undergo genuinely explosive strengthening within short windows of time. This year's especially early and powerful El Niño event adds another layer to that picture. El Niño conditions tend to redistribute where ocean heat concentrates across the Pacific, generally favoring increased hurricane activity in the eastern and central Pacific, while sometimes suppressing activity in the Atlantic. A pattern broadly consistent with what has been observed this season, with the eastern and western Pacific both producing intense systems, while Atlantic activity has remained comparatively subdued through the same stretch of the calendar. Seasonal outlooks issued earlier in the year had already flagged the potential for above-average Pacific hurricane and typhoon activity, given the early onset of El Niño conditions, and the string of powerful storms observed in recent days appears consistent with those expectations, even if the specific intensity and timing of any individual storm remains difficult to predict more than a few days in advance. None of this is meant to suggest that every storm this season will follow the same explosive path. Most tropical systems that form in any given year, even during an active El Niño year, remain relatively modest in strength, produce localized impacts, and dissipate without becoming the kind of headline-grabbing extreme event this particular storm has become. What makes this storm noteworthy is not that it formed. Storms form constantly during peak season, but the speed and magnitude of its intensification, and the fact that it has done so while multiple other storms across the broader Pacific Basin have simultaneously demonstrated similarly explosive behavior within the same general window of time. For anyone trying to make sense of what comes next, whether that's residents in areas potentially within an eventual forecast track, mariners and shipping operators routing vessels around the region, or simply people following the story out of curiosity or concern, the most useful approach is to rely on official advisories from national meteorological agencies rather than early, wide-ranging model tracks that can shift substantially day to day. Forecast tracks for powerful, structurally intense storms like this one tend to narrow and become more reliable as the storm gets closer to any potential point of impact, generally within about 3 to 5 days, which is why official agencies typically caution against overinterpreting long-range track guidance issued a week or more in advance. The technology behind these forecasts, satellite meteorology, computer modeling, and increasingly sophisticated data assimilation techniques, has improved enormously over the past several decades. But predicting the exact path and precise peak intensity of an individual storm several days out remains, and likely will remain for the foreseeable future, an exercise in probability rather than certainty. What we can say with confidence, based on the actual data collected and published by forecasters tracking this storm in real time, is this. A system that registered winds of 45 knots and a pressure of 996 millibars just days ago has since climbed through typhoon strength, approached and likely reached super typhoon intensity, and is forecast to potentially reach sustained winds in the range of 170 to 180 miles an hour, with gusts exceeding 210 miles an hour before any significant weakening trend begins. It has done so over a stretch of the western Pacific Ocean, where sea surface temperatures are running several degrees above the threshold typically needed to sustain a tropical cyclone, in an atmospheric environment offering low wind shear and abundant moisture, conditions widely recognized by meteorologists as close to ideal for rapid and sustained intensification. It has passed near Wake Island, prompting standard readiness precautions among personnel stationed there, and its longer range track remains uncertain, with model guidance broadly suggesting a path that could eventually bring it toward the vicinity of southern Japan or coastal areas of China, though the exact location and magnitude of any eventual impacts cannot yet be determined with confidence. It is also happening alongside, not instead of, other significant tropical activity elsewhere in the Pacific this same week, including a hurricane in the eastern Pacific that briefly reached Category 5 strength after its own explosive rapid intensification event, and a separate hurricane that had been tracking toward the vicinity of the Hawaiian Islands while gradually weakening. Taken together, these systems paint a picture of an unusually active stretch for the Pacific Basin as a whole, occurring during a year already flagged by seasonal forecasters as likely to produce above-average activity given the early and powerful onset of El Nino conditions. If there is a single takeaway from watching this storm's evolution over just the past several days, it might be this. Rapid intensification is no longer a rare footnote in hurricane and typhoon forecasting. It is becoming a recurring and central feature of how the most dangerous storms in any given season actually behave. A storm that looks unremarkable on a Monday can, under the right combination of warm water, low shear, and atmospheric moisture, become one of the most intense tropical cyclones on the planet by Wednesday. That reality places a growing premium on staying connected to updated official forecast information, rather than relying on outdated assumptions about how quickly or how slowly a given storm is likely to change. It also underscores why meteorological agencies continue investing heavily in satellite coverage, reconnaissance flights, and computer modeling capable of capturing these fast-moving changes in as close to real time as possible, because the gap between a storm that looks manageable and one that looks catastrophic can, as this storm has demonstrated, close in a matter of days. As the system continues its trek across the open waters of the Western Pacific, the situation remains fluid, and forecasters will continue issuing updated advisories as new satellite passes, reconnaissance data, and model runs become available. For now, the numbers speak for themselves. A storm that started the week as a run-of-the-mill tropical depression is ending it as one of the most powerful tropical cyclones observed anywhere on Earth this year, a reminder of just how much energy a warm ocean and a favorable atmosphere can pour into a single spinning system in a remarkably short amount of time. Whether this storm ultimately threatens a populated coastline or spends its remaining days spinning harmlessly over open water will become clearer in the days ahead. But its rapid rise from a weak tropical storm to a near Category 5 equivalent super typhoon has already secured its place as one of the standout weather stories of this particular stretch of the season, and a case study that forecasters, researchers, and storm watchers will likely be referencing for a long time to come. For those tracking the storm going forward, the guidance from meteorologists remains consistent with how experts recommend approaching any active, intensifying tropical system. Pay attention to official advisories rather than unofficial forecast maps circulating without context. Understand that forecast tracks, especially those extending 5 to 7 days into the future, carry significant uncertainty and should be treated as a range of possibilities rather than a precise prediction. Recognize that intensity forecasts for storms already displaying rapid intensification behavior can shift considerably from one advisory cycle to the next, and that a storm categorized as extremely dangerous today could either weaken through natural processes like an eye wall replacement cycle or land interaction, or could re-intensify if it continues moving over sufficiently warm water with limited wind shear. And finally, understand that even storms that never make landfall in a traditional sense can still produce significant hazards, from dangerous surf and rip currents along distant coastlines to disruptions in shipping lanes and aviation routes across the broader region. It is also worth taking a moment to talk about how forecasters actually gather the data behind numbers like these, because it is easy to assume these figures simply appear on a screen somewhere without much effort. In reality, tracking a storm like this one draws on a layered system of observation. Geostationary satellites positioned far above the equator provide continuous imagery, watching the storm's cloud structure evolve nearly minute by minute. Polar orbiting satellites pass overhead less frequently, but carry instruments capable of peering beneath the storm's outer cloud shield using microwave sensors, revealing the rainband structure and inner core details that visible imagery alone cannot show. In many active basins, reconnaissance aircraft, sometimes called hurricane hunters, fly directly into storms to measure wind speed, pressure, and structure firsthand, dropping instruments called dropsondes that record data as they fall through the storm toward the ocean surface. Where aircraft reconnaissance is not routinely available, forecasters lean more heavily on a technique called the Dvorak method, a decades-old but still widely used system that estimates a storm's intensity based on patterns visible in satellite imagery, comparing the shape, symmetry, and temperature of cloud tops against a standardized scale. References to Dvorak estimates in recent advisories on this storm, and to that consensus estimate increasing over successive advisories, reflect this exact process in action. forecasters continuously refining their intensity estimate as the storm's satellite presentation evolves. All of this data then feeds into an ensemble of computer models, some specializing in track prediction, some in intensity prediction, and some attempting both simultaneously, each running complex simulations of atmospheric physics forward from the storm's current observed state. Meteorologists rarely rely on any single model in isolation. Instead, they look at where multiple independent models agree, treating areas of strong consensus with more confidence and areas of significant disagreement, like the westward versus more northward track options discussed for this storm's possible path toward Japan or China, as genuine uncertainty that needs to be communicated honestly rather than resolved artificially. This is part of why official forecast products so often include phrases acknowledging that it remains too early to determine the exact location or magnitude of potential impacts, even days after a storm has become the center of significant public attention. It is not a failure of the science. It is the science being honest about the limits of what can be known several days in advance. Understanding that process also helps explain why the advisories on this storm have shifted somewhat from update to update, with intensity estimates moving between roughly 125 knots and figures approaching 155 knots within a span of just a couple of days. Those are not contradictory numbers or signs of unreliable forecasting. They are exactly what you would expect from a storm undergoing genuine, ongoing rapid intensification, where new satellite passes and model data can meaningfully update the picture within hours. The overall trend across every one of those updates has remained the same, upward. And that consistency, even amid short-term fluctuations tied to eye-wall replacement cycles, is what has kept this storm at the center of meteorological attention throughout the week. This storm's story is still being written, quite literally, advisory by advisory, as forecasters continue monitoring its structure, its track, and its interaction with the surrounding atmosphere and ocean. What began as a modest, almost unremarkable disturbance in the far eastern reaches of the western Pacific Basin has, within the span of less than a week, become one of the most intense tropical cyclones tracked anywhere on the planet this year. A vivid demonstration of how quickly the right combination of atmospheric and oceanic conditions can transform a weak system into a monster storm, and a reminder of why meteorologists, disaster planners, and coastal communities across vulnerable regions continue to treat every developing tropical system with the seriousness it deserves, right up until the moment it finally, and often gradually, spins itself out over cooler water or interacts with land and begins its inevitable decline.